Right. Lastly, what we were discussing about sequential search. Sequential search means like how can we search an element? So that is by like accessing all the elements in sequential search. So you need to access all the elements and check whether there is a exact match, right? So that is what we have done in sequential search. So okay, let me open the coding that we have done last day. Okay, let's create a new file. That is easy, right? So let's say you have a list, or let's say you have a file, anything. So what you need to do is you need to like start from the first item, search one by one, and then sequentially check whether there is a match. If there's a match, you can return that. If not, so you can return false. Okay, so let's define, let's have a list here. MK is kind of list having set of items. Let's say set of numbers. Okay, these numbers you have to search, and let's say let's write a function def binary search. Sorry, def sequential search. And you are going to give a list for the searching purpose. Let's give the list. Let's say search list. So that is the parameter. And what you're going to do for item in search list, and you have to give the item also, search item. For item in search list, what you can have to do is you have to check if this is if item matches the search item matches the search item with this, then you can so return true, and else you can return false. This will return true if item found. This will return false if item not found. So this function basically, so it's only showing you whether it's found or not, right? Then based on this, you can apply this function. Okay, first of all, let's say result is let's use the function sequential search. And I'm going to search on this list, MK list. The item I need to search, I can ask from the user, or I can just give it manually. Right? Let's give it manually. I want to search 90. You can see 90 is there in the list. If found, the result will be true. You can check that. If result is true, you can say search item print search item found. Search item found. Okay, so this is how you can apply sequential search function and do something. So this is basically your sequential search. The function is explaining the sequential search, and this is the application part, right? So this is actually how you applying sequential search function. Okay, let's save this. Sequential search py. Oh, don't use the same function name. That surely that will give an error. File save as sequential search example.py. Let's run it. Okay, when you run it, okay, whether if it is found, if MK is there, the 90 is there, yeah, this should, it should return. I think the problem is the file name that we have saved. We need to remove that file. Let's see. Okay, still no result. Sequential search MK. Okay, let's try this. I want to print the result. That false. I'm going to find 90. If for item in search list, okay, if item equal to search item, that part is also correct. So I have to store the result because this will return true and false in the for loop. Then what will happen? The first item, right? First item is it will return false. The second item it will return false. Third false, 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 true. Here it will return false, but after that again it will return false, false, false. So inside, this is inside the loop. You are returning false inside the loop. Hope you understood, right? Again, so this is like so when you are returning inside a loop, it will return true or false for each item. For the last item, what is the value? Is it true or false for the last item? Is it equal to 90? Is 67 equal to 90?
False.
Then so it will return false, right? That is why the false comes at the end. That is why the false come at the end. So to stop that, you can just store the found in a variable. For an example, so let's have a variable si search item or maybe result res. Initially, I'm making it. I'm going to okay. Let's say count equals 0. So if item found, I'm doing something like that. If item found, I'm incrementing count equal count plus 1. If not, I'm not doing anything. I'm just incrementing the count, right? Then when item found, the count should be more than 0. That you can check after the loop. After the loop, you can check if count greater than 0, then item found. Then you can return true. Else you can return false. Okay, this is the way, because return should happen outside the for loop. Then the return will only return based on the count. So now let's see. Now when I run the code, you can see what is invalid syntax. Else, let's run this again. And search item found. You can see. Okay, please copy this down. So please understand. So why we have not done this inside the loop. When we are doing this inside the loop, the returning statement will return false, because returning statement will consider only the current item in the loop. That is why. But so if it is found multiple times, that count also you can return. The count also you can return. So let's say 90 is there multiple times. 90 is there 2 times. Now you can return not just the true, you can return the count. You can return both this true and count. So then if result, so here you have to check the result 0. Result 0 is the true or false status. Search out item found, and then you can say how many times. That is result 1 times. So let's run this again, and now we can see, so it's returning search item found 2 times. Why? 90 is there 2 times. So it's returning true and count both. So this can be done. How many times the item is there? How many times we can just do that? Okay, when deleting item from a list, you can first search the item whether it exists in the list, and if it is exist, you can delete. Okay, let's say another 90 is there, then this should return what? Search item found 3 times. Okay, so see, it's counting. Okay, please update the code. Write down the heading is under sequential search. Please write down this. Sequential search. Right. The reason here,
this meeting is being recorded.
in line 16, bool object is not subtractable. Okay. Oh, you are checking. Oh, yes. So you are searching. You're searching for existing item. And if result 0, this is in line number 16, right? Is it?
Yeah, 16.
Yeah, result 0. So result 0, sequential search MKNO, returning true and count both. Exactly the same. Sequential search, search list, search item. You again count 0, item in the search list, item equal the search item, the count equal count plus 1. That is okay. Count greater than 0, right? You have to check count greater than 0, right? So you're checking count less than 0. Can you see?
Oh, okay.
Not there. So, yeah. Yes. Sorry. Yeah, there. Count greater than 0. Because when item found, please add, yes, the same place, yes. Please edit that. Count greater than 0. Otherwise, what will happen? Hello? Menaga, can you hear me? Yeah, count greater than 0. Please edit as count.
Hey, where is it? The hello?
Hello, yeah, count greater than 0. Just change it.
Hello?
Yes, the place you change is correct. The place you have changed is correct. That one.
Oh, okay.
Okay. So because like, you know, when item found, count increases, you have to check like that. Okay.
Okay.
This meeting is being recorded.
Now we are searching for item which is not there. So here, that is what I just want. So here it says the bool object is not subtractable. Here, can you return the count in the false part also? So that is the error, right? In the else part, yes, after false, please return the count. Even it is 0, doesn't matter. Just return that, because otherwise it will think this as a single variable. Now just run it and you can see you will not get that error. And in case of that, you have to say search item not found. That message I didn't mention, so you can add that. There means here if result is not there, else you can say search item not found. Right? Times is not necessary, because search item not found. Right? To do that, actually the count should be added here, and now no errors, and now it is running as expected. So when item found like this, when item not found, say 20, when it not found, it returns search item not found. Okay. Right, this is sequential search part. And there is another search called binary search, but so we have to consider this, like I'll tell you the concept, but implementation and all these things you can learn with future studies. I can tell you, but the thing is these are bit like algorithms. It's going like, so for normally we are teaching for the kids above 16, 17, but you can explore, right? Once you practice this, tell me, then I can teach you. because otherwise you will confuse with the things that we have learned. Anyway, so let me show that using small list and tell me what is the issue of this large list, right? And sequential search. For an example, 20. So if it is going to find 20, it search first item, the search second item, third item, fourth item, it's matching all the items. So it will be matching. So let's say there are n items, it's trying to compare with all n items in the list. But let's say this n is something like 1 million. If there are 1 million items in the list, so what will happen to the result? The result will be delayed because you have to compare with all 1 million items in the worst case scenario. That is called the worst case, when item not found. When item not found, still it will compare with all 1 million items. So that is 1 million comparisons. That will definitely slow down your that will definitely slow down your process or the software that you have created. To stop that, to minimize that, there is another sorting algorithm, which is a bit faster than this actually. So that is binary search. So let me show that interactive, using interactive animation. What will happen actually, the search list is divided. Search list is divided. Search list is divided to two parts, right? Search list is divided to two parts. Okay, here, see this. So when you are searching this list for binary search, so initially what will happen, the search list will be divided into two parts. But in order to binary search, the list must be sorted. If list is not sorted, it's not possible to use binary search. If list is sorted, already sorted in ascending, descending order, then you can apply binary search. But if not, you have to use linear search for the sequential search. Okay, let's try to search item 90 in linear search. See what will happen. It will compare first item, second item. You can see it's keep comparing the items and returns element not found, right? It's comparing all the items. And so it says element not found. So this is, so let's try for a large set of list or small set of list. Here the linear search, first item you're searching, so third item. All right. So why it is returning not found? The reason is list is sorted, right? List is already sorted. And let's say I'm searching for 1000. Let's say I'm searching for 1020. 1020 in linear search. See, first item, second item, all the items will be compared because this list is sorted. Let's keep on searching and searching all the items. So that is this is the worst case scenario. Worst case scenario, it's searching all the items. That is the linear search problem. Actually, since this is already sorted, the searching will be a bit easy because like if it is searching for an item in the middle or item in beginning or something like, okay, 70 is here, you can say, so it's the second item, it matches. The second item, element found. So how? Because while the index, so try to understand this, while the index less than length of list data, you are searching for the whole thing and up to the end of the list, and list index is less than value. So this should be list index less than value, right? So index plus, you are just incrementing. And if index is less than or equal to length of data or the list data index not equal to the value, return -1 then. So here it's returning -1. That means item not found. Right? That means you have index is less than length of less than or equal to length of list data, or length of list data, or list data index or length of data or list data index not equal the value. So that means the item is not there. So it return in false, -1. Otherwise, it's written in the index found. Written in the index means the found item. So actually this is a linear search. This linear search is basically discovering the item in the list. Okay, what will happen? I'm searching item 130 there. You can see the first item, index 0. Comparing index is incremented. So after that, so you can see the item value is not less than, right? While, so this is going up to when the item value is not less than. So that will stop in the middle. Otherwise, in our algorithm, so we have actually done for a list which is not having sorted data now. So this is a list, and this this is a list. This list items are not sorted. These list items are not sorted. Let's say you have sorted this list. Let's say you have sorted this list. For an example, you have this list, and let's say you have sorted mk.sort. So now let's print the mk, and this is a sorted list. Now, if you're searching, okay, if you're searching, let's say 60, you can search, compare this. No, not found. Compare this. No, compare this. 60, right? No. And then you can see at this time, you are checking whether the item is less than or equal less than 60. Then only you are searching. Is item less than 60? Yes, 56 less than 60, you can search. Then go to the 65. Is it less than 60? 65, is it less than 60? Hello?
It's more than 60.
It's more than 60. Do we need to search this list, or after that, or can we give up?
We can give up then.
We can give up. Why? Because after that, all the items are greater than 60. No point finding 60 in these items. You can give up. So that is the idea here. If it is less than the value only, you keep on increasing the index. So when you reach this point here, this is the idea, right? When you reach this point, when list index less than value and also less than the list data, that means up to the end you can go. So for an example, when I am searching 1020 in the linear search here, so it's checking the list index less than value, still less than. So because these values, all these values are less than 1020, all these values. So you can see the red color one. It's checking the red color condition. All these values are less than 1060. So it keep on indexing, keep on increasing the index. Keep on increasing the index. And finally, it will reach the end of the list because length of the data is less than. So this condition is reached. Therefore, it will come out of the loop. And then index is greater than the length of index, means this index is 0. So we have started with, this is like count variable that we have. It's checking whether is it greater than or greater than this length of data or this index of this value. So is it greater than this? And if it is greater than, that means it exceeds it. Either it exceeds the count. That means you have come to the end of the list but still not found. Length of data. Either it has exceed the count, or so list data index is not equal to the value. That means item not found. Either item not found in the middle, or it has exceeded the list. Then -1. In that case, not returning. Otherwise, you are returning the positive index that it found. But this one is not searching multiple items, right? When the first item is found, it says found. But if there are multiple items, this will not say there will be another item because it's not searching the entire list. Okay, I hope you understood the binary search concept for a sorted list. And also, sorry, I hope you have understood the sequential search or the linear search. Both are equal, right? Sequential search or linear search. Concept for sorted list and unsorted list. Did you understand? Or not? If not,
Yeah, I understood.
okay. So here in this one, the problem is it's not searching for multiple items, right? So it should be, so it's once found, it says found. If there is another item, it's not going to find that item. So if there's only one item, so it says found. Okay, then the binary search. Let's see the binary search. So binary search is very easy. Okay, it's not searching up to the end. It's not searching up to the end. So instead of that, it first take the first item, then check the last item. So first item index is 0, last item index is 31. Right? First item index is 0, last item index is 31. So it's taking these two indexes, C. Okay, first item index 0, last index is 31. It divided by 2, and the mid index is taken. And checking whether the mid item matches with the search value, right? So the 0th item, last item 31, mid item 509, is it matching with 1020? No. Actually, if so, which side is actually, so in which side you can find this data? Is it in left side or right side of this list? Let's say this is left side of the list and this is right side of the list. So 1020, the possibility of having 1020, will it be there in the right side or will it be there in the left side?
The right side,
Yeah, right side. Why?
because that's where the larger numbers are.
That is a larger number. Very good. So then can we drop entire list? Then can we drop this entire part? Do we need to search this part again? Or can we drop this?
We can drop it.
Can drop it. Okay, that is the advantage of half of the list. Let's say 1 million items are there. Then now after this incident, you have only 500,000 items. See, now you don't want to search 500,000 items. Out of 1 million items, 500,000 dropped. Okay, the second wave, second round. Again, you are reassigning the lower as 16, higher as 31. Let's see. In the next step, the lower will be 16 here. The higher will be 31. The mid will be 23. So then you are checking whether mid matches with the search element. Mid is 771. The search element is 1020. Let's say 1 million item was there. Now 500 items remaining. Out of that 500 items, now you have found the middle value. So 1020. So what is the higher possibility? Will it be there in the right side or left side?
Right side.
Right side again. So because it is larger. Then can we drop this entire list? This part? We can drop, right? We can drop this entire part. Now, previously 1 million item was there. Let's assume. Now you have 500,000 items. Out of 500,000 items, now 250,000 items. See, it is half now. So that is why it's called binary. It is half now. So how fast this is? If there are very large amount of items, see how fast this is. So now you have only this part because the other, sorry. You are searching this part now. It has 250,000 items. Again, you are checking the lower and the middle and find in the middle, check whether the middle matches with the element, and if not, search the right part, right? Subtree. Again, the lower and then so just find in the middle item where the middle matches that, and so again the higher and the lower and find in where the middle matches that, and you can see it's not. And this is the end of searching. So for any number of, for any search, so this is the maximum that you can go for any search. So there will be 4 or 5 levels. How many levels? Half, 1 level, then again half, 2 levels, again half. So let's count that. Okay, first half. Oh, sorry. First half. Okay, one search number 1. Second half, search number 2. Third half, search number 3. Fourth half, search number 4. And search number 5, it's over. Only 5 searches. Within 5 searches, it should find the item. Otherwise, the item is not there. Let's give an item. Let's give an item which is existing or not existing. Let's say 508. 508. Binary search. Okay, 1, 2, 3, 4, 5. It's all right. Only 5 searches. It's all. So that is the efficiency of binary search. Let's say 404, an existing item. Only 5 searches. Within 5 searches, it will find. So that is how efficient this is. Let's say, luckily, if you say search 509, the first search itself, it will find. That is the middle item. You are lucky, element 4. This is the best case. You guess the best case is the first middle item is the item. That is the best case. The worst case, this item is not there. So can you understand now why the binary search is efficient than linear search? Hello?
Yeah, I do understand it.
Okay. But the problem is what? What is the problem of this searching? Binary search, what is the main issue?
It takes it takes a long time.
Binary search? Binary search will do it within short time. So think that there are a million items, it will make it half, again half, again half, again half, again half, and do this faster. Binary search is
okay.
faster. For large number of items, binary search is faster. So what is the drawback issue? Can we apply this to a non-sorted list?
Oh, no.
No, we can't apply
We
this.
can't.
That is the problem. Linear search can be applied for both sorted, non-sorted, but binary search can only be applied to a sorted. So that is the problem. Okay. Our next algorithm. So now we know few algorithms. We learn searching algorithms. So, and we learn how to find max minimum. Those are also algorithms. We found how to find the total in a list. That is also an algorithm. Now in this attempt, let's try to sort the list. So you know it's very easy to sort. So if you give sort, it will sort. Right? If you just give the sort function, it will search. Sort. But the thing is, we need to develop an algorithm to sort. Okay, let me do that first. Please write the heading there. Sort in algorithms. Sort in algorithms. That is the heading. Sort in algorithms. So I think you know the concept of algorithm now, right? Algorithm is basically built in a way, a systematic way. Creating a systematic way is called an algorithm. Right. Sorting algorithms. So under that, we are going to learn a few sorting algorithms. So one is bubble sort. Bubble sort. So why this is called bubble sort? It is like interesting way. So let me show you animation first, then let's do the implementation, right? So this is bubble sort interactive, right? Please understand that already there are ways of sorting, there are ways of searching. These are already there, right? Already developed. Actually, we don't want to write that from the fundamental level. But just to understand programming, we do this. Right? They are already developed. So if you just use the sort function, it is sorted. You might wonder why we need to learn them. So because mk.sort will sort. If you want to search, you can just say let's say if 56 in mk. So see how easy. If this is searching, right? If it is 56 in mk, you can say print found. So how easy this is. Why do we need to learn search algorithms, right? Because this will say just found 56 in. So this is very easy operation. mk.sort. This is very easy operation. But why do we need to learn an algorithm to do this? Because we need to train our brain. Right? I think you have seen forces trainings. They are just moving through the barriers. They are running in the ground, but no real enemy is there. In the forces training, they are just shooting a dummy. Shooting a dummy, maybe running through barriers, jumping and maybe climbing. So why? You might think, so if there are no enemies, why should I do this? It's the training, right? It's the training. Similar to that, this is a training, right? So that is why we are doing this. Okay, let's go to the visual goals. So this has very interesting animation set. And see here. So it explains us what is happening there. Okay. So I need to learn bubble sort. So here, unsorted list. In the bubble sort, so please try to understand what is happening. I will give this as a homework to develop the algorithm, because you have to also try this now. Tomorrow we can discuss about that. Okay. So in the bubble sort, it will just compare the adjacent items. It's like a wave. It's like a waveform in ocean. So a wave is generated and it will be propagated. A bubble is generated and it will be propagated. First, you are checking these two items. Whether, so if you want to sort this in ascending order, the small item should come to the left side, the large item should come to the right side in ascending order. Then it's checking these two items. If the left item is greater than the right item, it swaps. If left item is greater than the right item, it swaps, right? Okay, let me start. See, so it's checking. Oh, it is too fast. Let me slow down the process. Sort again. So see, it's first checking these two items. Is left item greater than the right item? Is left element greater than right element?
Well,
left element is
it's
3, right element is 44. Is left element greater than right element or not?
no. Right element is greater.
Left element is not greater than right element, so no swapping. No swapping involved. The second type, is left element is greater than right element? No?
Yeah.
Yes.
Yeah.
Now you need to swap. Now you need to swap. Swap means you have to change the positions of the left element and right element. Let's see. It's changing, right? Next, again checking. Is left element greater than right element?
Yes.
Need to swap, right? Need to swap. See, swaps. The next, what will happen in the next? Will it swap or not swap?
It will not swap.
Yeah, it will not swap. Next two, this two.
It will swap.
Next two will swap. Next two will swap. Next two will swap. Next two also. Next two also. And next two also. And the next two also. So what about next two? Will it swap or not?
It will stay the same.
Keep as it is. The next two will swap. Okay,
Yeah.
as the result of this, can you see the largest item in the largest item in this list is propagated, or it will be floated to the end of the list, end of the first round. Is the list sorted now? After this, is this list sorted?
No.
No.
You
Then
need to
what
run
you
it
have to
again.
do? You have to start the process from the beginning. Beginning again. See, so it is doing the same process again. The first largest item now in the corner, now doing the same process to the next set of items. Swapping if the left element greater than the right element, and keep on moving if the left element is greater. Okay. This way it's trying to find the next element. Now the next element. So it is applying the same process, propagating the large element to the end. Swapping happens if the term violates, that means left element cannot be there if it is larger. Okay, done. The next round. So you can see this way the list is slowly sorting. Okay, done. The next. So it needs multiple rounds. It's not easy. It needs multiple rounds. Okay. Right now, so still not over. You can see the initial part of the list is not sorted. It's reapplying the process. Okay, you can see after no swapping, now there are no swappings, and so this is sorted. Actually, what you can see here, this is called pseudocode. This is not the actual code. This is the pseudocode. Don't write the code. This code won't work. But this will give the structure. By looking at this structure, can you just give a try? By looking at this structure, can you just give a try to create a Python code to do the same? Just look at this code and try to make a Python code to do this process. So this is a bit challenging, I know, but just give a try. I'll help. This is not real code, right? This is a structure, code structure only. only a pseudocode. But looking at this, you can try to convert that to a Python code. Just give a try. Okay, I'll give the initial guidance, but you need to continue with this, right? And you need to continue and do this as a homework. But I'll just give the initial guidance, only the initial guidance, right? So let's say there is a list like this, right? Let's say there's a list like this, and so you can say, okay, def bubble sort. In this bubble sort, getting a search list similar to the previous, getting sort list, and so you can say do means you start doing, and you can just say instead of that while true. That means you start doing. While true means you always do. What you're saying, swapped equal false, but you don't have this simple false in Python, so instead of that you have capital false. So swapped equal capital false. Okay, then for I equal 1 to index of last unsorted element minus 1. So that is basically, you can say, for in range, you can start from 0 because you know the first index is 0, and 2, you can say length of the search list, length of search list minus 1. For I in range 0 to length of search list minus 1. Okay, then what you need to do? If element, right element, left element, that you don't have something called right element, left element, that you need to find, right? You know the right element. So this can be, you can say if this search list, so here left element, no, left element is 0. Actually I 0 means left, first time I. Then what is the right element? That is search list. You can say I plus 1. That is the right element. Search list I plus 1. Okay, I think now you can do that, right? The remaining part. Can you? Is it difficult? Just mapping these with the.
I will.
Sorry.
I'll try.
Yeah, you have to map these with the relevant Python code, right? When there is a pseudocode given, what you need to do, you have to map that with the relevant Python code. Then the swapping part. Swapping part means you are replacing the right from the left, left from the right. Variable changing, just changing the variable. For search item I, you have to assign search item I plus 1, and then search item I plus 1 is equal to I. That you have to swap. You can use intermediate variable, maybe temporary variable, because if you have coffee in one glass or one mug, and tea in one mug, you know how to swap coffee and tea. How can we swap? If you need to put coffee into the tea mug and tea into the coffee mug, how can we do that? You need extra mug, right? That is your temporary variable. Then you can put coffee into this. Now coffee will be here, and it's not here now. So then after putting that, you can put tea into this. Here you will get tea now, and this one will be empty. Now after this, you can put the coffee this way. Now we have swapped the coffee and tea marks. Understood? Using a temporary. Similarly, this swapping can be done. You can use a temporary variable and swap. Okay, just give a try. Just give a try. Tomorrow you can give a try. Let's do the remaining thing tonight. Okay, and good night. Bye.
Bye.